Okay, so this is the second practice paper for periodic table elements and physical chemistry. So we start off with our multiple choice. So first one off, we need to find a correct equation for the enthalpy change formation of copper 1 iodide. Okay, so remember enthalpy change formation, the definition is to form 1 mole of the compound using the elements in their standard states. So it's got to be D for that one. Obviously it's copper 1 iodide there, so it's going to be Cu plus I minus, hence the formula CuI. Right, for question 2, you've got to do a little bit of maths. So we know that the formula is XO2. So the amount of element X is 14.4 grams. Because the total compound has a mass of 24, then I know that 9.6 grams of it is oxygen. So I find the moles of oxygen, which is 9.6 divided by 16, which gives me 0.6. Now, because it's in a ratio of 1 to 2 there, I know that the corresponding amount of corresponding moles of X is going to be 0.3. So 14.4 divided by the molar mass of X is 0.3. You rearrange that to find the molar mass as being 48. So it's going to be titanium if you then look at your periodic table. So the answer's C. Alright, for question 3 we're going to do a little bit of maths as well. So how many bromine molecules are present in each decimeter cubed of air? So I have got 0.004 milligrams of bromine per decimeter cubed in the air. So that is obviously going to be in grams. You have to convert that into grams, which is 0.40 times 10 to the minus 3. You then need to divide that by the molar mass of bromine. The relative atomic mass of bromine is 79.9, so times by 2 is 159.8, and then finally you times that by Avogadro's number, which you will find on your data sheet, and if you do that you will find the answer to be A. Okay, so we now need to work out which element has the largest atoms. So we're going to first of all look at the ones in the highest period, and that's period 4, which contains both potassium and calcium. Potassium ends up in 4s1 and calcium ends up as 4s2. And then finally, which one is going to be the largest out of these two? Well, it's going to be potassium, because you've just entered into that fourth shell. So you have the fewest number of protons holding on to those outer electrons. Remember, the shielding will be the same for both potassium and calcium, but calcium has more protons. So the answer is going to be B. So for this one, we're going to do a little bit of Hess cycle. So just remember that you've got 3 NO2s there and 2 nitric acids there. So you have to times this number by 3 and this number by 2. I put the values over the arrows here and here. Okay, and then you put it into your equation to work out delta H. Do a bit of rearranging and you should get the answer to be B. Okay, so we're now going to work out what happens when I halve the concentration of hydrogen. So the new rate is going to be proportional to, so you've got a half of what you had for H2 times double NO, which is going to be 2 squared. So that's a half times by 4, which is equal to 2. So the reaction rate will be doubled, which is C. Okay, so they've told us that the half-life here is 2 minutes. So that means that the concentration of AB will halve every 2 minutes. And I've got to work out the concentration after 6 minutes. So first of all, what is the concentration of AB initially? Well, I've got 0.1 mole. That's in 100 centimeters cubed. Times it by 1,000, so it's going to be 1 mole per decimeter cubed. So let's halve that, so it'll become a half, so 0.5, then it'll become a quarter, which is going to be 0.25, and then it will become an eighth, which is 0.125 moles per decimeter cubed, so the answer is C. So for the next one, we're going to use Le Chatelier's principle. We're going to compress this at constant temperature. So first of all, Kc will always stay the same if temperature remains the same. So the answer is either going to be C or D. However, what's going to happen to the amount in moles of methanol? Well, if you have a look on this side of the equation, you've got 3 moles of gas, but on the right-hand side, you've only got 1 mole of gas. So if you compress it, you're going to shift the position of equilibrium towards the product. So therefore, the amount of moles of methanol will increase. So the answer is D. Right, so moving on to question 9, we've got to do a buffer calculation. So I popped in our buffer equation there. So pH equals pK plus the log of the concentration of the base over the acid. Now they told me the Ka there, so I can easily work out the pKa of methanoic acid, which I've done as being 3.76. And then if the concentration of the base is half that, the concentration of the acid is half the concentration of the base, then it's going to be 1 divided by a half, which is of course 2. And so that becomes log 2, and if you work out that equation you get it to be 4.07, so the answer is D. Okay, so for the next one it's asking me about the following statements regarding for a neutral solution at any temperature. Notice that's for any temperature. So Kw is only equal to 1 times 10 to the minus 14 at 25 degrees C. So that is not true at any temperature. The solution contains only water molecules. That is also incorrect because we know it's dissociated, partially dissociated. C is correct because if it's neutral, the concentration of the acid must equal the alkali. And pH is equal to 7 only under standard conditions, 25 degrees C, and therefore the answer is C. Right, so for question 11, you have to make sure you balance it with respect to oxidation numbers as well. So you can see the copper has changed oxidation state by 2, but the nitrogen only by 1. So therefore you need to times the nitrogen by 2 so that you get the same change in oxidation state. Now if you do that, you now have to check your oxygens. So on your left hand side you've got 6, but on the right hand side you only have 5. So you need to put a 2 in front of your water there, which means you need a 4 in front of your H+, so the answer is B. So we now need to decide which property is not correct for calcium. And A is it acts as an oxidizing agent, which is of course not correct. It acts as a reducing agent because calcium becoming calcium 2 plus is itself oxidized and therefore it will reduce something. So the answer is A. Right, so question 13 then. What's the reaction at the negative electrode? Okay, so silver is going to go that way because it's the most positive, which means this one is going to go that way. And that's going to become the negative electrode. So the answer is B, which is that one there. So question 14, X is a particle of 18 electrons and 20 neutrons, which could be X. Well, neutral argon would have also 18 protons, so it could be that one. For number 2, calcium 2 plus, that has also got 18 electrons, but it would have 20 protons, so that could be correct. And potassium plus would have 18 electrons but 19 protons. It would have let's get that right. Potassium plus would have 18 electrons and 19 protons, and 19 plus 20 is 39, so that could be correct as well. So the answer is A. Alright, so a few mole questions now. So for question 15, first of all, let's work out the moles of zinc for this one, and it's 0.05. So because zinc to zinc chloride is 1 to 1, you would produce 0.05 moles of zinc chloride. Okay, you've now doubled the amount of zinc, so double the amount of zinc, double the amount of moles as 0.1. So, and that amount of HCl is 0.1. However, it's a 1 to 2 reaction, so actually 2 is incorrect. Right, and now you've times that, you've doubled that again, so you've now got 0.2 moles of zinc. So you would make 0.2 moles of hydrogen. So 0.2 times 24 is 4.8. So again, 3 is not correct either. So actually the answer is D. Only 1 is correct. Okay, so moving on to section B then. So we're looking at electrons in boxes for an oxygen atom. So an oxygen atom obviously has got 6 electrons in the outermost shell. So we're going to fill up the 2s first, and then you're going to put the rest of them 1, 2, 3, 4, like so in the 2p. Okay, then looks at successive ionization energies for electron structure. So that's for shells. And they've gone all the way from the 1st to the 11th there. First of all, they want us to do the equation for the 7th ionization energy of sodium. So you start with Na6 plus in the gaseous state to produce Na7 plus in the gaseous state because they want the 7th ionization energy. Why do they get larger as we remove electrons? Well, that's because the radii of the ions is going to decrease. You've got the same number of protons, but you're attracting fewer electrons every time you remove one. And therefore the attraction between the nucleus and the outer electron will increase. Explain how successive ionization energies provide evidence. Well, if you have a look, there's a large difference between the first and the second, and also the 9th and the 10th. You see a big jump there. And that shows that you have entered a new shell. So obviously you remember from GCSE, your electronic configuration, just looking at shells, is 281. So that represents moving into this shell here, and then that represents moving in to the shell closest to the nucleus there. Okay, so for part C, or rather part 4, let's have a look at that. So the trend in first ionization across the periods gives further details on electron structure. Explain how the first ionization of magnesium and aluminium give this detail. Well, if you remember, aluminium's outer electrons are in the 3p subshell, which is higher in energy than magnesium's outer electrons. So magnesium ends in 3s2, but aluminium has 3s2, 3p1. So I've entered a new subshell there, and the 3p subshell is higher in energy than the 3s. Therefore, it takes less energy to remove it. Right, so I've now got to deduce the possible identities of my two ions there. So I'm looking for an A3 plus ion and a B2 minus ion to get those charges to work out. So if it's A3 plus, I've got to add 3 electrons to that electronic configuration, and that would give me scandium. And then if for B, I've got to remove 2 electrons from the outer electrons, and that would give me a sulfur. So the ions are scandium 3 plus and sulfur 2 minus. I've then got to calculate the empirical formula of that salt. Getting quite straightforward. One of the first things you would have done at AS or perhaps even GCSE. You take your percentages here, divide by the relative atomic masses to get this ratio, then divide by the smallest one, which would be that, to give you this ratio in whole numbers. Now, it's an organic acid. So an organic acid is going to obviously have the carbons, but you've got nitrogens in there. So you're looking at having NH4 plus, because you haven't got, if it's an organic, sorry, if it's a salt of the organic acid, you need to have some metal ion or ammonium there, and you'll notice you haven't got any metal present there. So NH4 plus, and then you need to work out what you've got left over. So you can have CH3COO minus, like so, and that should all work out nicely. Right, it's question 17 now, and this is looking at enthalpy changes of solution. So it's given me, once we do the dot and cross diagram for calcium chloride, obviously that's going to be a dot and cross diagram, which I have done below, showing ionic bonding. What's meant for the term enthalpy change of solution? This is when 1 mole of a compound dissolves in water. Okay, now if we go back to the previous page, you will notice they've given me some enthalpy changes. What I've done is I've popped these onto the table, onto the chart here, to give me the diagram. So obviously the reverse of lattice enthalpy going up here is going to be your ions in the gaseous state. The first change is the enthalpy of calcium being hydrated, hydration of the calcium ion. And then the second is the enthalpy of the chloride ion. You have to times that number by 2, of course, because you've got 2 chloride ions. And then you pop that into your equation, your cycle, rearrange it to find delta H solution to be minus 142. Basically, this side here has got to equal that side there. Right, so we now need to explain these differences in enthalpy changes of hydration. So basically we know that the higher the charge and the smaller the ion, the higher the attraction to water molecules. And so let's just have a look at these ions. Well, first of all, aluminium has got a higher charge than all of them. So it is going to be higher. So aluminium is larger than magnesium, has a higher charge than magnesium, which has a higher charge than sodium plus, like so. And then when you look at calcium and magnesium, the calcium ion is going to be larger than the magnesium ion, because obviously calcium is in the next period down. Okay, so we now want to work out some enthalpy changes here. So once delta H solution for calcium chloride, and they've given me all the measurements in the table here. So first of all, work out how much energy went into the water, then work out how many moles of calcium chloride you actually used. It looks like cobalt chloride, doesn't it? Calcium chloride there. And then delta H is going to be your energy change, and I've converted that into kilojoules by divided by 1,000, divided by your moles. Remember, it's a minus figure because your temperature went up, because it's an exothermic reaction, and they're to 3 significant figures, because your temperature's to 3 significant figures, you get minus 132. Okay, so D part 2 is quite interesting. Student 2 carries out the same experiment but uses twice the mass of calcium chloride. Predict any differences between the temperature change and the calculated value of delta H solution. Okay, so you use twice the mass of calcium chloride. That means the temperature change will be double up here, but your number of moles are double up there. So when you divide those two numbers together, because that will obviously have increased, you get the same value for delta H solution. So twice the energy will be produced in the same volume, and so the ratio of energy produced to mass or number of moles is going to be the same. Okay, so question 18 is a bit of a gift really. So it gives me the old Haber process, which we all know and love, and it wants me to talk about the operational conditions to give the maximum yield. Okay, so let's have a look at this. How are we going to get the maximum yield? Well, first of all, pressure. I've got 4 moles of gas that side, 2 moles of gas that side, so if I use a high pressure, the equilibrium will be pushed towards the right hand side, which has fewer gas moles on it. Temperature. Well, the forward reaction is exothermic, as demonstrated by this number here. So you want to use a low temperature to favour the forward reaction. Okay. However, so those are two. You want a low temperature and high pressure. However, a low temperature will give you a very slow rate, and a high pressure is expensive and also produces a safety risk. So you have to have a compromise for both temperature and pressure. Finally, catalyst. Catalyst is all good, really. It means that the reactions will take place at a lower temperature, so you have a lower energy demand, which reduces costs and also reduces CO2 emissions if you're using fossil fuels. Okay, so that's pretty nice and easy for 6 marks. Okay, so now I'm going to put some maths into this. So let's have a look. The way I like to start off is I write initially the equation and then the number of moles that I start with. Now, if you have a look, I produce 0.36 moles of ammonia. So that means because it's a 1 to 2 reaction, I must have lost half of that amount of nitrogen, which is 0.18. So 0.8 minus 0.18 gives me 0.62. And then you times that by 3 and you've lost 0.54 moles of hydrogen because it's a 1 to 3 reaction. So that's the number of moles that you end up with at equilibrium. You then have to convert that into concentrations by dividing by 5 decimeters cubed, which I've done. Pop that into your Kc expression and you find it to be 0.812. Now, in order to work out the units, you need to really substitute the units into the equation. You end up with moles per decimeter cubed to the squared over moles decimeter cubed to the power of 4. That's going to cancel. That's going to become squared. And so it's 1 over that, which gives you those units there. So the key thing for part C is you're keeping this at 300 Kelvin. And I am adding more nitrogen to that. Now, you can't use Le Chatelier's principle here. They want you to use Kc. So let's have a look at this. Kc must remain the same because the temperature is remain the same. If you increase the amount of nitrogen, that number is going to get bigger, which would obviously adjust Kc. So the equilibrium has to adjust to produce more ammonia. And in order to produce more ammonia, it means that some of your hydrogen is going to be moved up. So you need to talk about Kc will not change with pressure or concentration. And therefore, as the N2 increases, that would change your value of Kc. And therefore the H2 must react with the N2 to return the value of Kc to its original value, which means that the chemist was correct. Suggest why the chemist is more concerned with increasing the proportion of H2 that reacts rather than nitrogen. Well, it's because nitrogen is obtained from the air and hydrogen must be manufactured. It doesn't occur naturally. Okay, so we've got to find out our rate constant. So first of all, we need to find our rate equation. So let's have a look. So if I look at experiments 1 and 2, I've doubled the concentration of ozone, and I've tripled the concentration of ozone, and I've tripled the rate. And therefore it is first order with respect to ozone. And now if I have a look at 2 and 3, I've doubled NO2 and I have doubled the rate, so it's first order with respect to NO2. So my rate is equal to my rate constant times the concentration of ozone and the concentration of NO2. Okay. So now I need to determine my rate constant. So you can use any of these experiments if you like. So if I use experiment number 1, my initial rate is going to be 3.20 times 10 to the minus 8. Divide that by my concentration of ozone, which is 1 times 10 to the minus 3, and my concentration of NO2, which is 2.5 times 10 to the minus 3. And if you do that, you end up with the rate constant as being 1.28 times 10 to the minus 2. How about my units? Well, my rate, of course, is in moles per decimeter cubed per second. Concentration in moles per decimeter cubed. So the overall units are going to be in moles to the minus 1, decimeters cubed, seconds to the minus 1, like so. Okay, so we now need to look at a two-step mechanism. So my rate determining step involves ozone reacting with NO2 to, well, hopefully give me one of my products, which could be O2 plus NO3, like so, which is going to be an intermediate. Okay, let's just make that more obvious, NO3. Okay, I've got to get rid of that NO3, so then my NO3 could react with my other NO2 that I haven't used, plus NO2 is going to give me my other product, which is N2O5, like so. And then that should all work out nicely. Okay, so I think we all know where this question's going. So first of all, we just need to calculate those two remaining values of 1 over t and also log k, or ln k. So we've done that. And then we're going to plot a graph. So I put the equation there. So remember, we plot a graph of log k against 1 over t, and then you will end up being minus EA over r. So your gradient, so I plotted the graph there, your gradient, the difference between your values here and here, minus 6.84, difference between these values here, 5 times 10 to the minus 4. If you do that, you end up with it being 6.84 divided by 5 exponential minus 4. You get that as being minus 13680. Now obviously that is equal to minus EA over R, so you need to times that by your gas constant, which is times 8.318314, which is on your data sheet. Divide it by 1,000 to then convert it into joules, and obviously you're going to change the sign. So that gives you an activation energy of 114 kilojoules per mole. Right, so you've got to be a bit careful here because they changed the question midway through. So let's just go. First of all, why are the pH values of nitric acid and nitric acid different? Well, nitric acid is a weak acid, and so HNO3 is a strong acid and HNO2 is a weak acid. Now, be careful here because it says calculate the value of that concentration, but it shouldn't be. There's an error. It should be 0.0450 there, and the same goes for that. Okay, but don't worry too much. Okay, so if you do that, you'll end up with a pH value of 1.35 using this equation. Obviously, for HNO2, it's a weak acid, so you first of all need to find out your concentration of H+. Using this equation, the square root of Ka times your concentration, which I've done here, and then pop that into your pH equals minus log to the base 10 of H+, and you get a pH of 2.35. Okay, so part B, rubidium hydroxide, I need to prepare a solution of pH 12.5. So how much rubidium hydroxide do we need to use? Well, first of all, we need to work out, we've got our pH, so from our pH we can work out the concentration of H+ ions. Once we've done that, we can use our Kw expression here to work out our concentration of OH minus ions. Now, because there's one hydroxide in one rubidium hydroxide, that is also going to be the concentration of rubidium hydroxide. So that would be how many moles you would have in 1,000 centimeters cubed, but you only need 250. So if you divide that by 4, you find that you need 7.91 times 10 to the minus 3 moles of rubidium hydroxide, and then times it by 102.5, which is a molar mass of rubidium hydroxide, to find out you need 0.810 grams. And then you're going to balance a redox equation here. So we've got to be careful. First of all, we work out our element which is oxidized. They've told me that it reacts with sulfur to form sulfuric acid. So the oxidation number of sulfur is going to be 0 there. In sulfuric acid, H2SO4, it's going to be +6. Nitrogen goes from +5 in nitric acid, and in nitrogen dioxide it is +4. And then if you notice you've got hydrogens here, so it's like you're going to end up with water on the other side. Now you need to balance it. Now we've said that the nitrogen goes from here to here, it goes from +5 to +4, so that's a change of -1. But sulfur there goes through a change, let's have a look, a change of 6 rather. So you notice I made a little bit of a mistake there. So that should not be SO2. That should actually be, let's get rid of that, H2SO4. So let's change that to H2SO4. If I can, H2SO4. And now the oxidation number of sulfur there is going to be +6. So you've got to times the nitrogens by 6 to get your oxidation states to balance, like so. And that means to get your hydrogen to balance, you need 2 waters. So let's write that out, because I made a bit of a mess of that, didn't I? So 6HNO3 plus sulfur goes to H2SO4 plus 6NO2 plus 2H2O. Job done. Okay, so we now have a question about chromium. So first of all, we want to work out the electron configuration of chromium as an element. Now remember, chromium is one of the odd ones in that you have 1 electron in a 4s subshell and then 5 in the 3d. It halves, puts your electrons half in the 4s and half in the 3d, so they're both half filled. Then when you do the plus your oxidation state, you're going to lose your 4s completely and you're going to lose 2 from 3d. So it's going to be 3s2, 3p6, 3d3, like so. Okay, fine. Next on to B, we've got an empirical formula as so it contains 1 chloride ion and a complex ion J, which has 2 stereoisomers. So I've got to draw those. So if you look, you've got N4H12. So N4H12 works out quite nicely as 4 ammonia ligands. You know one of those chloride ions is going to come out, so that means you've got 2 chloride ions combined to the cobalt. And as you know, if you've got that sort of arrangement of ligands, you can have a cis isomer where the chlorides are together and a trans isomer where they are opposite each other. Okay, so part C then. We have got various tests that we need to now consider. I've got 2 compounds of transition elements and I need to work out what they are. So I am adding ammonia dropwise, and this is really where learning your transition element chemistry will really help. So your first one, you've got A and B. When you add ammonia, you get, first of all, a green precipitate, which when you add excess becomes a violet solution. And that is shouting out to you that it is chromium 3 plus. For B, you've got a pale pink precipitate and then no further change, and that suggests you have manganese 2 plus. And I put the equations down here. Again, this is just transition element chemistry that you need to really know. And now you need to work out your counter ions. Well, first of all, you add barium nitrate and you get a white precipitate for A. So that suggests you have got a sulfate, and you have got a yellow precipitate when you add silver nitrate for B, which suggests you have iodide. So that means your formulae are going to be a Cr2SO43, and also they're going to be MnI2. Okay, almost there. So why do we add nitric acid in tests 2 and 3? Well, nitric acid will remove any carbonate ions, which if you had those present, they would form a white precipitate with silver plus and barium 2 plus ions. So that would make it very difficult to work out whether you had any other counter ions there, because you'd always see a white precipitate if you've got carbonate there. So that's where you add the acid. Student 2 accidentally used HCl instead of HNO3 for both test 2 and test 3. What different observations would student 2 obtain? Well, for test 2, there wouldn't be any difference at all. But for test 3, you would see a white precipitate of silver chloride being present. And so what would you actually see? For A, you would see a white precipitate. For B, you would see a white-yellow precipitate. And finally, how could the procedure be modified to be more certain of the conclusions? Well, as you know, when you're testing for halides, ions, once you've made the silver halide precipitate, you add ammonia solution. So you'd add concentrated ammonia, and the yellow precipitate of silver iodide will not dissolve.